All right, do you remember back in high school, middle school, when you were first introduced to the quadratic equation, right? And you were basically uh, told that when you have a quadratic formula or that or quadratic equation of the form ax squared plus bx plus c equals 0, as long as a doesn't equal 0, obviously, because you don't have a quadratic at that point. This is a way for you to quickly find the roots, right? The roots meaning the zeros or the x-intercepts. It's a quick way for you to be able to figure out what values of x would make your equation equal 0. Okay? And for many of you, probably even to this day, have the quadratic formula memorized. But it does work. I'm like you. I would rather factor if I can, but I always have that in my pocket if I can't factor something, so that I can still figure out the solutions. All right, still figure out the zeros. But maybe we can at least appreciate that you probably have never had to use the cubic formula for finding zeros, right? For finding roots, or the quartic formula for finding those roots. They all work, right? It's all, I mean, if you have, again, if you have cubic equations of the following form, or fourth degree equations of the following form, it's just a matter of plugging in A and B and C and D and E. But you can see that the work does get quite, well, it is quite involving, right? I I grabbed a few of these formulas online. I have worked through these formulas, you know, many moons ago when I was in college. Clearly, we've actually had access to the cubic and the quartic formula for probably since the 16th century. Um, but I haven't. I grabbed a couple pictures online just to throw up, just so you could see what they look like. I have not even, I can't even read what I posted here. So, so don't get mad if you fact check me and you figure out that there's something wrong with the picture I put up. What you can at least take away from this is, hey, if I want, if it doesn't factor, right? Look, in textbook problems, everything factors nice and neat. But if something doesn't factor correctly and I want to try to figure out the zeros, well, uh, if it's a quadratic where every life is okay, right? But if it's a cubic or a quartic, things can get a little bit messy. Well, Newton had a fairly good technique for ways of approximating the zeros. Now, today, our approximation techniques normally take the form of let's look at the graph or do a table on our calculator. And actually, that's very awesome. But Newton had a pretty amazing method for just approximating the zeros, right? Not exact, but just some approximations that we're going to go through in this video. Okay, so how does Newton's method work? So give me just a second here. So the idea consists of the following. So can you and I agree that the x-intercept is here? That's the 0. I would like to be able to find a good approximation of that 0, and I want to be able to do it without using, let's say, some of those very time-consuming formulas. So what is a way that I can get a good approximation of a 0? Now, we will assume that you've already we have already been guaranteed that the 0 must exist, right? We can use the intermediate value theorem to show this. But once all of those conditions are behind us, how did Newton do this, right? Because How did Newton work this? It's pretty genius when you think about it. So, in essence, this would be Newton's technique. Take a guess. Right? So notice this x sub 1 right here this is a guess. I don't know what the true x-intercept is, but I'm going to just take a guess. And now, once I've taken my guess of x sub 1, if I plug that x sub 1 into whatever function it is that I'm dealing with, right, then the y value, so look at point A, the y value would be f of x sub 1. And now here's the method. So f of x is the function, say, that Newton had that he wants to find the x-intercepts, the zeros, the roots. He can, at this stage, take a derivative of that function. That's not a problem. And so if you take the derivative of that function, plug in the same x sub 1, so we would be plugging in that same guess into our derivative, we can get a slope. Now with a point and a slope, can you and I agree that I can always get a line? And this line is going to run tangent to that point A. And here's the genius part of it. So in the beginning, remember, this is what you want, right? Let's just go to take a trip down memory lane for a second. You're in the 17th century. You want this value. So the method is take a guess at something close. Use that point and the slope at that point. Draw a tangent line, which I did, all the way to the x-axis. And now look at the genius of the technique. Do you agree with me that I'm closer in distance to the true x-intercept than I was when I took a guess? Right? I'm closer. Now, how would you do better than this? Well, now, remember, x sub 1 was your initial guess. Now this would be x sub 2. And what do? Well, you play the same game. So point B is going to be x sub 2. This is the new guess. Find out what the y value is. Now the y value in this case would be all the way down here, so I'm not going to be able to do all of this. Find the slope. Draw another tangent line. And every time you draw another tangent line, right, you're going to get closer and closer and closer to the true x-intercept. In fact, after you've ran about 3 iterations of this method, you are very close to the actual x-intercept. It's a genius technique, very clever technique for finding zeros. So let me go ahead and make a few statements. So I'm going to show you how to use this approximation technique in just a second. But the basic idea is take a guess, run an iteration. Whatever comes out, use that new value, and then run the iteration again. And it's just, you're just running iterations after iterations until you're as close as you feel that you need to be. Okay? Whatever margin of error that you're willing to accept. Okay, so I'll make a comment in just a little bit about when Newton's method fails, because sometimes it does fail to work. I tell you what, I'll just go ahead and say it right now. It's actually that when you run the tangent line, the tangent line has to run to the x-axis. right? So if your tangent line at the curve, let's say the tangent line looked like this, well, it's never going to cross the x-axis. You're not going to be able to use Newton's method. It would fail to work in those conditions. So there are a few stipulations. Again, there's a few things that you have to consider before you start, but instead of going through all of those preliminaries, I just want to show you the approximation technique. Ready? So I'm going to leave this here for just a second, but instead of me reading it to you, we're just going to jump in and do a problem using Newton's method for approximating the zeros of a function. Just remember, mathematicians, they tend to use words like zeros and roots and intercepts, x-intercepts. They are not synonyms in the sense that they do have different meanings, but they are, for the most part, we're all talking about the same idea. So an x-intercept is actually a point, whereas a zero is just the x part of that point. Nevertheless, no more talking. Let's get into the method. Okay. So it says calculate 3 iterations of Newton's method to approximate the zero of the following function. Now, I know that you already know how to find the x-intercepts of x squared minus 2. Okay, I get that. I'm just going to show you this technique on a baby problem, and then I'll show you how you could use it on a problem that is much more difficult. Okay. So how does this work? Well, the things that you're going to need are obviously the function f of x, which was given, and you're going to need the derivative of that function. Okay, so in that case, it's just 2x. So here are some things that you're going to need. And now let me go ahead and create some columns. So the next thing that you're going to need is your initial guess. Okay, so everything you're going to see this subscript n show up a lot, but the basic idea is the initial guess is your x sub 1. That's your first round of approximating. So now in this case they actually tell us, right? So this is the n. They tell us to use 1. So this is going to be x sub 1. This is our first, my apologies, let me erase that. So this next column is just going to be your x sub n column. So when n is 1, we have x sub 1, right? And what are we told that x sub 1 is in this problem? Well, x sub 1 is, we are told our initial guess is 1. Okay, so with n is 1, x sub 1 is 1. That's our initial guess. Okay. The next column is going to be f of x sub n. Okay. Since I'm only going to do one of these, I just want to make sure you understand that that means in this case, we're going to plug in 1 into the original function. So if you plug 1 in for your original function, you would have 1 squared minus 2, which is equal to negative 1. All right, now, then you're going to take your x sub n and plug it into your derivative function. So since our x sub n is our initial guess, that's 1, we're going to plug that 1 into our derivative. So 2 times 1 is 2. So f prime of 1 is 2. All right, so the next column is going to be to find the quotient of these two. So it's going to be f of x sub n divided by f prime of x sub n. So let me go ahead and write that. So this would be f of 1 divided by f prime of 1. So in this case, we would get negative 1 over 2. And the last column, which is the column that I'm grading, is going to be for you to take x sub n minus the result from the previous column. So minus f of x sub n over f prime of x sub n. Okay, so you're just going to subtract. So ready? Let's go ahead and do this. So what is x sub n in this problem? It's 1. So 1 minus what? Well, what is f of 1 divided by f prime of 1? Well, it was negative 1/2. So you see how we're just taking this result and bringing it here. So that ends up being 1.5, 1.5. So that is your first iteration. And what we know is, I don't know what this x-intercept is yet. We'll figure it out in just a second. But I started at 1, that was my guess, and now I'm at 1.5, and I'm closer. So since we were asked to do 3 iterations, now we're going to start our second iteration, x sub 2. So what are we going to use for x sub 2? Well, you're going to use whatever you got from the previous column. So now do you see how the game just starts over again, right? It's the same iteration. It is just a matter of finding a slope and a point and running a tangent line to an x-axis. That is what we're doing. All of this fancy notation is that. Now, you should probably add a few more decimals than you're used to, right? Normally, most students either round to the nearest whole number, or maybe they go out a couple decimal places. But since this is an approximation technique, and so let's go out. You should go out a few decimal places, 4 decimal places at least. So what I'm going to do right now is just fill in the values. You can take 1.5 and plug it in for f, and 1.5 and plug it in for f prime. And you can double check my arithmetic to make sure I'm doing everything correctly. But we should get 0.25, 3, 0.0833. I'll go out 4 places. And then my sincere apologies, I cannot read my handwriting, it's so small. I think that's 49. No, I think that's 41. 4166 is what I think we got. 4166. All right, so that's the second iteration. We would have one more iteration to do. So now your new guess is 1.4 6, 6. We're getting closer and closer to the true x-intercept. So let me now see if I can just fill in the rest of these values. So this would be 1.41. My apologies. I can't. It's very hard for me to read my handwriting at this point. I think it's 0.0069. Then 2.8333. Then 0.0024 and 1.4142. All right, so let's take a look at this 1.4142. What we rounded, but that is after 3 iterations of this method. That is our approximation. Now, let's go back to the function. F of x is equal to x squared minus 2. Now, listen, I'm guaranteeing you that Newton was not using this method on functions this simple, right? Newton would have simply, if he wanted the if he wanted to know the x-intercepts, the zeros, he would have set it equal to 0. And we would get x is equal to plus or minus the square root of 2. And now what you should do, let's just go ahead and look at the square root of 2. What you should do is, if you have a calculator on your cell phone or available, do me a favor. Take the square root of 2 on your calculator and then compare it to your approximation. You're pretty darn close, okay? And we only went out 4 places. We could have gone out a few more places if we wanted to see how close we are. But after 3 iterations of this method, you're pretty darn close to your 0. All right, so fairly amazing technique. I've already explained to you when Newton's method does break down. By the way, just in case you're interested, there's no formulas for, like, there's quadratic equations, cubic equations, quartic equations. There is no formula for any polynomial that is a 5th degree or higher, right? We have formulas for quadratics and cubics and 4th degree polynomials. There is no formula for 5th degree polynomials or higher. In fact, it's been proven that you cannot use radicals to solve for the zeros, right? I believe it was probably the early 18th century, if I can get my math history in my head correctly, but a couple of mathematicians actually, by the name of Abel, I believe, Abel's impossibility theorem. As always, fact check me, because I've been out of school for a while. All right, ready? So here's what I want you to do. I want you to allow me to read this problem for you and to set it up like we were going to go through all the steps and solve it, okay? But I want you to allow me to just give you the derivative without showing you the work, and to give as well as give you the function after you set the derivative equal to 0 without showing you all the work, because I'm more interested in telling you how Newton's method could aid you, how you could use it as an approximation technique. So, ready? You are in a boat, right? You are in a boat, so here's you in a boat 2 miles from the nearest point on the coast. So you got 2 miles. to the nearest point on the coast. Now, you are to go to a point Q. Here we go. So here's the party, right? Point Q. That is 3 miles down the coast and 1 mile inland. So in other words, the point Q is 3 miles down the coast, but you're going to have to walk on land a little bit as well, so we have 1 mile inland. Now, you are you're a thrill seeker, obviously, but you know that you can row your boat 3 miles per hour, and you figure that you can walk on average at 4 miles per hour. So the question is, you're here on this boat. Where should you land, right, on the coast, so that you can reach your point Q, the party, in the least amount of time? Right? I mean, should you land your boat here, or here, or here, or here? Do you see how this is an optimization problem? This is an optimization problem that you don't want to try to find the critical numbers of. So let's you and I agree. We'll kind of start to walk through this quickly. Let's you and I agree that your distance is equal to the average rate divided by time, right? In other words, if you tell me on average how fast you were going, and you tell me how long you were going that average rate, I'll tell you how far you went. I'll tell you the distance. So what we're going to do is we're going to set up the idea that, so since distance is equal to rate multiplied by time, we want time, right? That's what we're trying to minimize in this problem. So if we solve for time, so d is equal to r over t, that would mean that t is equal to what? T is going to be equal to, well, I'll go ahead and do it so I don't do any silly mistakes. So t times d would have to be equal to r. And finally, time is going to be equal to rate over distance. All right. So time. So I can write time as the following. Did I do that correctly? I think I did that correctly, right? Distance, so distance is equal to, I know what I did. I messed up. Do you see these problems I'm having right now? What I meant to say. So distance is equal to rate multiplied by time. Let me stop looking at my handout. Distance is equal to rate multiplied by time. Time is equal to distance divided by rate. Whatever I said prior to that, I'm not going to edit it. My stupidity will remain. Okay, distance is equal to, time is equal to distance divided by rate. Okay, so ready? So let's set it up this way. So time is going to be the distance that you are in your boat rowing, divided by the rate at which you can row. It's funny, I've made so many videos in the last few weeks. My voice is starting to go. My mental capacity is starting to wane. We also have the distance that you walked divided by the rate that you can walk. Okay, let me eyeball this for a second just to make sure I didn't do anything Silly? So if you want to know how much time it took you to get to point Q, well, it's going to be the amount of time you spent in your boat plus the amount of time that you spent walking, right? And what we're doing is we're writing time as distance over rate. Okay. So in this case, it's pretty easy let me go ahead and fill in the rates, right? Because they were given to us. So I know the distance that I can row is 3, and this is in miles per hour. And the distance that I can walk is 4, so that's 4 miles per hour. The distance, though, so if you take some arbitrary point X, let's assume that you land here on shore, well then you can label one of the legs of the triangle to be X. Obviously the other leg of this right triangle is 2 because you're 2 miles from shore. The distance is simply going to be the hypotenuse of this triangle. Does that make sense? Now, the other triangle, well, you are 1 mile inland. You would have to, from the coast to point Q. And since you're 3 miles, we know the distance is 3 miles down the coast. Whatever you choose for X, this is going to have this leg of the triangle is going to have to be 3 minus that, 3 minus X. So do you see how the distance is simply these hypotenuses, right? Does that make sense? All right. So that would be 2 squared plus X squared is equal to that hypotenuse squared. So you would take the square root of that. So we'd have the square root of X squared plus 4. And then finally, again, you would have to, whatever this distance is, the second distance, it would be 3 minus X squared plus 1 squared. The square root of that would end up with the square root of X squared minus 6X plus 10. Okay. So that is your time function. And now notice that it's a function of distance. Well, here's the part where I'm going to get to the point. So since this is an optimization problem, you want to minimize time. Here is the derivative of t without any more elaboration. And now, if I set my derivative equal to 0, and I try to start the process of solving for x, here's what I get. I get 7x to the 4th minus 43x cubed plus 43x squared plus 216x minus 324 is equal to 0. Now, isn't it nice that most textbook problems all factor perfectly nice, neat in their whole numbers? But if anybody's ever done any consulting work, anybody who's done anything in the applied world will tell you that it doesn't work out like that in real life, right? Life is messy, and you end up with messy functions, but you still want to figure out what x values would make this equation equal to 0. Now, let me show you how Newton's method could help you. So do you realize that at this stage right now, you could just start Newton's method? And I'm just going to fill in the values. I'm not going to go into detail here. So in this case, remember, Newton's method says that you got to take for your x sub 1 should be a guess. Well, let's take a look at the picture. So we know if we let this be 0, then this point would be 3. So we're trying to take a guess. How about, I think what I have on my paper is a 1.7. Okay, now what I'm going to do is just plug in the numbers that I got when I ran this through. So f of 1.7 would be 19.5887. And f prime would be 135.6240. The quotient of those would be 0.1444. 1444, yeah. And finally, when you do your guess minus that, it's 1.55. Let me write this with a little bit more space here. You end up with 1.5556. How does this help you in any way? Well, this is a good approximation of how long it's going to take you to get to this party. It's going to take you, since everything's in miles and per hour, it's going to take you about 1.5 hours to get there. Well, I don't know how important this party is, but if you wanted to continue, you could take that 1.5556, start your new guess, and do the iteration process again. But do you see how after one iteration of that method, you were able to find the approximate 0, which is the same way of aiding you in finding where your minimum amount of time. So my apologies. What I should have said is 1.556 is where you should land on it. That's approximately where you should land. You would still have to plug it in to find the time. I don't know what I said. That's 1.55 hours. So 1.556 would be a good place to go if you were trying to minimize the amount of time to get to point Q. All right, my throat's going. I'm leaving you guys. This is Newton's method. See you soon.